Welcome to our Quantum Deep Dive. Today we are diving headfirst into the fascinating and, yeah, let's be honest, pretty mind-bending world of quantum-enhanced data encoding. And all of this is based on a really detailed essay by Jörg O. Schneppet.
Right, so here's the plan. We're going to start by looking at the limits of our current data systems. We're calling it the classical data wall. Then, we'll get into how quantum mechanics offers this totally revolutionary new way forward. We'll cover the tools, the techniques, the amazing applications, and, of course, the very real challenges before we peek into the quantum future.
Okay, so let's kick things off with a problem that really affects every single one of us in this digital age. Doesn't matter if you're a data scientist or just trying to stream a movie, we are just creating data way faster than we can actually manage it.
You know, there's actually a name for this. It's called the curse of dimensionality. And it's pretty simple when you think about it. As our data sets just get bigger and more complex, adding more and more features, our traditional algorithms for storing, processing, and analyzing all that stuff, they just can't keep up. They don't scale well, performance just grinds to a halt, and we end up hitting these fundamental walls with our memory, our bandwidth, and our processing power.
Right, and let's get into the nitty-gritty of why that is. Way back in 1948, this brilliant guy, Claude Shannon, he gave us a mathematical formula for information itself. And this equation you see for entropy, it is not just some abstract theory. It defines the absolute unbreakable speed limit on how much we can compress a piece of data without losing anything. It's a hard, physical law that pretty much governs our entire digital world. Yeah, and here's the kicker. In the classical world, you are always making a trade-off. It's a constant battle. You want more precision in a scientific model? Okay, but you're going to need way more storage and processing time. Want to compress that giant video file to save some space? Well, that's going to require a ton of computation. And if you want to protect your data from errors, you've got to add redundancy, which, you guessed it, makes it bigger again. It's these trade-offs that create these bottlenecks that we just can't seem to get around. But what if we could play by a completely different set of rules? A set of rules that honestly seems to defy our everyday logic. Well, this is where it gets really interesting. This is where quantum mechanics comes in, handing us this powerful new toolbox to just smash right through those classical walls. Okay, so the foundation of this new toolbox is something called a qubit. Now, a classical bit, that's simple. It's either a 0 or a 1. A qubit, though, its state is described by that state vector. It can actually be a combination of both 0 and 1 at the same time. And those symbols alpha and beta, you can think of them as complex numbers that tell you the probability of finding the qubit in either state once you actually measure it. And that is superposition. It is the absolute key that unlocks an incredible amount of power. So, think about it. If you have n classical bits, they can only represent one value at a time. But a system of just n qubits, it can represent a superposition of all 2 to the n states at the same time. That's not just a small step up. That is an exponential leap in how much information you can pack in. And then things get even weirder. There's entanglement. Einstein himself called it spooky action at a distance, and for good reason. It's this non-classical connection that links the properties of qubits together. So if you measure one, you instantly know the state of its entangled partner, no matter if it's across the room or across the galaxy. This creates this incredible information density, tying parts of a system together in a way that's just, it's completely impossible in our classical world. All right, so we've got these incredible new tools, superposition, entanglement, awesome stuff. But now for the big question. How do we actually use them? How do we take our normal classical data, our images, financial models, sensor readings, and translate them into the language of a quantum computer? Well, it turns out there's not just one way to do it. The whole process is called Quantum-Enhanced Data Encoding, and researchers generally use 3 main strategies. You've got amplitude, basis, and angle encoding. And of course, each one has its own pros and cons, which makes them good for different kinds of data and different quantum algorithms. And this table really lays out the trade-offs perfectly. On one hand, you've got amplitude encoding, which is, in theory, the most powerful. It crams an exponential amount of data into just n qubits. The catch? Preparing that state is super complex and needs really deep quantum circuits. Then, on the other end of the spectrum, basis encoding is simple and tough, but it doesn't hold much data. And right there in the middle is angle encoding, which is this kind of flexible, practical sweet spot that's really popular for the early-stage quantum machines we have today, especially for machine learning.
Okay, so we've gone to all this trouble to encode our data into a quantum state. The big question is, so what? Why does this even matter? Well, the payoff is, and this is no exaggeration, potentially enormous. It could unlock brand new capabilities across a whole bunch of critical fields.
Take the world of AI, for example. Quantum encoding basically acts like a super-powered feature generator. It can take your data and lift it into this incredibly high-dimensional space. Think of a tangled-up ball of yarn. That's your data. In this new space, that ball of yarn suddenly becomes a set of straight, easily separated lines. This means we could potentially solve problems in classification and optimization that are just completely impossible for classical computers today. It could totally revolutionize machine learning.
And the security advantage is just brilliant. With quantum encoding, you can build communication systems where security isn't just based on some hard math problem that a powerful enough computer might solve one day. No, it's guaranteed by the laws of physics. There's something called the no-cloning theorem, which means a spy can't just copy a quantum state without messing it up. And that disturbance, it's immediately detectable. This makes things like quantum key distribution fundamentally, provably secure.
Now, all of this sounds absolutely revolutionary because, well, it is. But we have to pump the brakes a little and be realistic here. We are still in the very, very early days of this technology. There's some huge hurdles we have to get over before this vision becomes a reality for everyone.
And the main problem is the massive gap between the perfect qubit we imagine on paper and the real ones we have today, what we call NISQ qubits, for noisy intermediate-scale quantum. See, real qubits are just incredibly fragile. The slightest interaction with their environment, a tiny vibration, a change in temperature, causes them to lose their special quantum properties. This process is called decoherence, and it is, without a doubt, our biggest enemy right now.
So you see, the race isn't just about building more and more qubits. It's really a race for quality over quantity. We have to build better, more stable qubits that can hold their quantum state longer and have fewer errors. And just as important, we have to design encoding methods and algorithms that are clever enough to work around all the noise that we know is going to be there in today's hardware.
Okay, so even with all those challenges, let's look ahead. Because the vision for where this technology is going is, well, it's truly transformative.
Just imagine this. As we slowly but surely move from today's noisy machines to fully fault-tolerant quantum computers, this whole encoding process, it's just going to become a seamless, automatic part of the operating system. A developer won't even have to think about it. A smart compiler will just look at the data, look at the task, and pick the perfect encoding strategy all by itself. And the long-term impact of that, it's going to be felt everywhere. We're talking about truly unbreakable encryption, AI models that can discover new drugs or design new materials, problems that are just impossible today. And we'll see a new world of hybrid computing where classical and quantum computers work together, each playing to its strengths. This is why it's such a strategically important technology for, well, everyone, countries and companies alike.
You know, when you boil it all down, the key takeaway is this. Quantum-enhanced encoding is not just about building a faster computer. It is about developing a completely new way to represent and interact with information itself, at the most fundamental level possible. It's like we're learning a new language to describe reality, and we're all just starting to figure out the grammar.
We really hope this deep dive has given you a good look into this incredible, fast-moving field. And if you want to learn more, you can read the full essay by Jörg Owe Schneeppert that this whole explainer was based on. Just head over to schneeppert.de. Thanks for joining us, and goodbye for now.
Schneeppert.de is a private project by Jörg Owe Schneeppert dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.